Hello, everybody. My name is Chester Chen. I'm the Senior Manager of the Data Science and Engineering at GoPro. I'm also the founder and the organizer for this meetup called the San Francisco Big Analytics. Currently, we have about 4,500 members. Previously, I have worked on the different companies, large and small. Before that, I was working at Alpine, particularly in Alpine Data Labs, Semantics, and other companies. I just joined the company, GoPro, recently. So I've been working with Spark since 0.6, but the majority of my work with Spark is during our Spark integrations at Alpine Data Labs, and we have been integrating from Spark 1.1, 1.3, 1.5, and different versions on different Hadoop distributions, Cloudera, HolonWorks, and MapRs. So since I just joined the GoPro, so I probably put one or two slides for GoPro. So GoPro is more than just a company, right now. So we have both services and different data sources from different areas. And so we have distribution channels from different social networks, and we have drones and different logs from different places. And so there's a lot of data coming from our data pipelines, and so I'm kind of excited to be helping building the data pipelines. But today's talk is about real-time machine learning visualization with Spark, and this work is mostly done before joining GoPro at Alpine Data Labs. So to start with, I want to just talk about one particular machine learning algorithm, K-means, and because I'm going to use that as a demo and also discuss some of the concepts. So just briefly, what is K-means? And this is directly copied from the Wikipedia. And essentially, you have a set of operations, and then the K-means try to partition the data into different clusters, and it's a K clusters. And each clusters, you want to measure the distance and try to minimize the distance. So you essentially define a cost function in that equation there. So visually, you basically, in this case, for example, we're taking like a public, really well-known data sets, ARIS data sets, and with the K-mean with the three clusters, 0, 1, 0, cluster 0, cluster 1, and cluster 2, and each one have a centroid, and seats the three different circles. And the distance we measure is really just the distance between one data point to the centroid of that cluster. So what we want to see is a kind of I want to see what the cost function have been changing during the training process. And so from iteration to iteration, so what is the cost going down, or doesn't, is it generally plateaued, or that doesn't converge at all? So our goal is this, machine learning training is experimental. So basically, sometimes you need a lot of experimentations, and some trainings actually take a long time. So we want to use the visualization to determine whether I want to end the training. So can I end the training early? If it's already converged, why keep it still going? If it is, I want to kind of also monitoring the process into a convergence and clustering or any residual plots and see during the training process. And I just sometimes if I see already plateaued, even though the training is still going, but I think I can just stop there and changing some other parameters in just or totally different algorithms. So collect the model then. So and then sometimes because you enable this visualization, adding additional costs, so sometimes you're deciding to enable or disable this visualization at any point of the training. So with that, I want to do a quick demo here. So yeah, I don't see why I don't see the video here. You don't see the QuickTime movies I'm trying to show here. Oh, here. So I'm not quite sure how to do this. Now I couldn't see myself. Okay, all right. So this is the, oh shoot, let's from the beginning. Let's play a little bit. It's very hard for me to do this way. And try to put the cursor here. Okay, all right, it's going. So, so this is the Alpine's workflow engine's visual editor. So I'm basically here. Usually, when you training a machine learning model, you usually have a lot of steps. Building the pipelines and building the workflow. So you have the original data, and you have a bunch of transformations that eventually end up connecting to a machine learning algorithm. In this case, K-mean. In this experiment, since I'm basically just trying to do a demo, so I skipped all the intermediate steps, essentially directly connecting the data sets to K-means. And the data sets here I'm using is airplane data, which is available publicly. So when the machine learning start running, so I'm basically, the data set is about 10 gig, and I have set the K-means for max of 20 iterations. I don't know if you can see what the properties I said earlier. So when I start running, and so you get the tracking URLs from the yarn, and then you can directly click the, make it faster. So 2 times? Okay, a little faster. So, so the tracking URLs, which has different links, and some of the links can directly to link the Spark UI. Some other links can directly go to the cluster logs, and others is links that directly give you 2 panels to allow you to visualize. So during this time, I'm examining the Spark UI, see what's going on right now. At the beginning of the training, so before the K-mean algorithms kick in, and he actually doing the data samplings and then the early MapReduce and try to get the data before the actually K-means kick in. So you notice here we integrated with the callback, so the Spark redirected the Spark listener to sending the messages direct to our UI. So all the links you see is actually staging information of the Spark and directly display in our cases. Let's see. So here I'm just examining the log and try to see how much memories and how many cores in the log. And each stage is a tracking URL. You can click on the UI in any times. Anyway, at about 4, let me see, couldn't see that what the time steps right now. So it's about 4 minutes times, and then the K-means the iterations will kick in, and then you'll see the visualizations. So I'm placing 2 graphs. Oh, now you can see that now. So we're having 2 different views of the clustering. So one is the arrival time versus the departure time. The other one is distance versus arrival times. So you can see different times. On the bottom, you see the cost versus the iterations. At each iterations, the cost going down. You can gradually see that the cost has been almost plateaued, even just a few iterations. So at I think about 8 or 7, close to 10 iterations, and then you're getting pretty good model already. So even though I have set to a 20 iteration max, but at this point you probably just you see that I click the stop iteration. That means I got a good enough models. Just save the model and then stop running. And then I check the log just to make sure that message the stop iteration message being passed. So at this point, the Spark will finish the rest of the rest of the stages, and then our program will save the model in the HDFS. And then you notice that at the end of iterations, actually we see a sliding bar there that allow you to replay the history, the iterations. You can actually slide back and forth to see how at each iterations you can see the centroid have been slightly changing because the cost is dropping pretty quickly and then pretty plateaued. So from other use cases you may not get that. You can see probably dramatic changes by changing the sliding bar. So okay, so that's the demo. Let's see, let's go back to this. So how do we achieve this? And I'm not really trying to show that to show the Alpine product. Basically, I want to see what you can do. And then these are the basic steps you can do in your own systems, in your own jobs. So essentially, this involves into 4 steps. And first, we need to define a callback interface for Spark machine learning algorithms to send messages. So the algorithm itself will decide when and what message to send out, but it doesn't care how the message got delivered. And the other one is a task channel whose basically show purpose is handle the message delivery. And he doesn't care what's the message and what's in it. Basically, he's try to sending the message from the Spark driver to the calling program, the Spark client. So these two steps essentially determine from the cluster sending to outside the cluster. But once the outside the cluster, you need to send over to the browser. So there's messages. In this case, you either using pull or push. In this case, we're using push. So the push method we're using here is using server send event SSE and also the HTTP chunk response. It was essentially that forming a streaming push, and then we'll discuss the push and pull later in the later slides. And then finally, we're using the D3 and Plotly to do the visualizations. So here's another overview of just what I talked to. So in the general Spark programs, it's something like this. But in this particular case, we're talking about Spark. We're using young cluster mode for Spark. So for young cluster mode, essentially the Spark job can be initiated from the REST API, from servlet, or command lines from Spark shells, and talking to a client program. And the client essentially launch the programs, and the Spark driver essentially launch the young container, and inside the driver, inside the container, drivers launch the Spark jobs, and there you have the Spark contacts and your machine learning algorithms. So in our case, we want to control how this is being run. So we actually establish a communication channel. So before every Spark job starts, we actually start as application context. The application context defines a messaging logger. And also, when the Spark is submitted, we also submitted a URI, which is specify which host I'm sending this, I'm calling from, which port you want to call back. And once they called in, the programs actually do a handshake. So establish the communications. And from then on, we can send any kind of messages over. So we're actually using this communication channels to send messages like a log. For example, the log you usually see on the Yarn log, we actually redirect it to our application log outside the cluster. And we're also sending the UIs. You see the tracking URLs for Spark UIs and all the other Spark UI, usually Spark UI stages displayed on our UI, we send it over. We also send in application status, send it over so you can directly update counters on the UIs. So there's it's a general communication channel, so we set it up. So in this particular case, because we're talking about real-time visualization for Spark machine learning, so basically here is machine learning algorithms go through an interface called the machine learning listener, ML listener, and the ML listener sending specific messages to the logger, and the logger send it out, and that push to the browser. So something like this. So the message being sent to the Spark client, the Spark clients push the messages to the REST API layer, the server layer, the server, and the server layer you're using chunk response push to the browser, and the browser essentially using visualization tools to visualize. Okay, so let's dive even more details on each part of it. So the first part, we're talking about the machine learning listener. Okay, so we mentioned that we need a callback interface. And so essentially, interface is quite simple. So here I'm using Scala syntax. The following piece is going to have a lot of code, so bear with me. So the first one is ML listener. So it defines a simple message. You say on message, and you do something. Okay. So and the other interface is basically listener support. ML listener support essentially have a message and say send messages. You passing a message, and then if you said it's enable this listener, we simply go for each listener we call on messages. It's very simple. So for k-means, because we have to deciding where to send the message during the iterations, so we have to modify the k-mean extension. Hopefully, Spark in the future have some hooks built in, so we don't need to do this kind of things. But here, we have to extend the k-means, we call it k-mean extension. And we're mixing this listener, ML listener support trace, we just defined earlier. And for k-means algorithm, essentially come down to this one piece of function called run algorithms. And here is simply a loop, while loop. And basically, the bold pieces is the part we changed. The gray pieces is what the Spark originally has. Essentially, the while loop basically saying is if the iteration is less than max iterations, and then this active run is not empty, just continue to run it. So in this case, we're basically adding one flag and say if you give me a flag and say stop iterations, it's not stopped, and then you continue around. So that allows me to control when to stop the loop. And the other part is if listener is enabled, just call the send message. And the send message is inherited from the machine learning support interface directly. So, and the message I send, each algorithm is different. For k-means, basically, I'm care about the couple of things. One is, what's the iteration right now? Okay, so that's the iteration integer. The second part is, what's the cost associated with this iteration? And the third one is, what's the centroid of this k-mean algorithm? So that defined a case class called the k-mean core stat. And so that, I'm basically construct that and then send it over at each iteration. So that takes care of the algorithm part. But for k-means, the ML listener just essentially a trade or interface. So the actual implementations for the listeners each could be different for each one. In this case, I'm constructing the k-mean ML listener. So notice here, when I receive a message, the on message call, I got the message I just described, the cost, the iteration, plus the centroid of the data. So before I do anything, so I first take a sample of the data. I basically here take 100 points data. And then for that 100-point data, I first take the centroid and construct a k-mean model and use that k-mean model to predict which these data, the sample I'm just take, belong to which cluster. So that gave me the sample data plus the cluster associated with the data. And then I construct the rest of the message and send it over through this logger. This logger is the places later on I will describe. So here I'm just constructing the message and send it over. How the message is delivered, this doesn't care. So the framework will take care of that. So I set change the machine learning algorithms, and I change the machine learning listener. And then now I need to set it up to, if I want to run this algorithm, so how do I set it up? So again, the original, ML lib k-mean algorithm, you basically you say new k-means, and you set the number of clusters, you set, the epsilons, you set the max iterations, and then you just say run. But here we need a little bit more. So we need a passing flag set whether we want to enable the listener, because sometimes we don't want to enable the visualization. We want to turn on and off. And the other part is we want to add the listener, which is defined. We say add listener for new k-means. And then on top of that, I mentioned earlier at the beginning, we also create this application context for every Spark jobs, and I didn't define there. In there, I add a task observer, which I'm explaining just a second. So once I construct this, and you can just run as usual, and then that triggers the rest of the program. So what that is a machine learning task observer. We described how to send the message, out, but we also want to receive commands, from the outside programs while the machine learning is running. So this task observer essentially is responsible for, to receiving command and notify the changes. So that has a trait called task observer. Basically, it has a notify method in taking an update task command. And once you got that task command, and again, you just do your things. So this is kind of that's all on the server side that you need to do. And if you want to say, okay, what about the other machine learning algorithms? Here is a similar change for logistic regressions. You change the logistic regression extends the ML listener support, and in that case, we basically have a train method which is run this OWLQN run method. Essentially, is something like this. And in that method, you construct a cost functions and then pass the cost function to some iterations. And the only difference is here I'm passing this machine learning support interface into that cost functions. And the reason is in that cost functions, there's a method called calculate. That is called at each iterations. So here I'm simply saying if I should stop, I'm just collecting the method, send the message over, and if not, I'm just continue to run. So in this case, I'm keep sending the messages. Here the messages is just iteration, the loss, just like the cost, the loss there, and the weight of the factor, and then the state. So essentially the same things. On the visualization side, essentially instead of plotting the clusters and then plotting the residual plots for the convergency. So same thing, linear regression, almost identical. Okay, so that takes care of the first part. Okay, next part is how do we communicate back to the Spark client. So here's the overall pictures. So when the Spark, start to run, so before they actually invoke the Spark, we create this application context. Application context create two things besides the normal Spark context and do the normal tasks. We also create actor systems. So the messaging we send it over so using Akka messaging. So I'm not quite sure you're familiar with Akka messaging. Akka messaging is a messaging system based on actors. Instead of making a function call, you're sending a message to the other end. The other end called another actor. Almost like a mailbox. You're sending a message over. He got a inbox, get something, and they start to processing that, and you do a pattern matching on what type of message it is, and you do certain things. So in this case, all the messages sent over is Akka messaging. So when the programs on the client program send message over, you basically essentially sending Akka messaging URI. Essentially, that tells what the Akka messaging base URLs, including the host and the Akka port and the actor path, and then they do the handshake. So here, when the Spark starts the actor systems, in that created two actors. One is a messaging actor, which is essentially our wrapper for the logger, and the other one is a task channel actor whose main responsibility to receiving Akka messages. So when we get these messages, when we send these messages, we send a message logger, which is essentially sending the Akka messages. When we receiving update commands, we're using task channel to in turn update the ML listening flag, and that basically controls the iterations, the flow, the while loops, where to stop. Okay, so that takes care of the messaging. Now, the message is already in the Spark client. So how do I push to the browser? So again, we're still using Akka messaging pushing to the REST API servers because we're using Akka-based REST API server called the Spray. So the message is sent it over to the other side, and the other side uses the chunk response to send it over. So So there's a combination of this server-side events, SSE, also called event sourcing. So it's pretty simple on the JavaScript side. Essentially, you define event source. You pass in the URI for your REST API, say, new event source, and that has a callback, and just say, giving whatever functions. The only things you need to be careful is there's a specific data format. It's usually, say, data colon, and then your strings. And string is ended with new lines. So so on the server side, you use this HTTP chunk response. So basically, because the Akka message, essentially you send the data, you get an event, and the event you just directly send to it. So in this case, when you start the program, when I click and say visualize, that start the chunk response, get to the server side and get chunk response. From then on, I'm starting sending, each time I receive a message, I'm sending a chunk. And then when I finish and I do chunk message end, this way, so they essentially a stream continue to send over without the browser pull for it. So, okay, so you say, well, why not just pull? You could use pull. So there's a pros and cons using push. So push, data is streamed, it's pushed to the browser, with each time. So there's no need for a data queue. You got the data, you push to it. But the data is got to be lost. If you don't use it, you got lost. And you can have multiple views. If, like for example, in this case, in the airline data, I have 2 views side by side. If you want to say, I want to see multiple dimensions and different, A plot against B, C plot against D, and you can have just multiple views, and then this data just directly pushed to all the views, and you got different presentations. The problem is there's also downside. For a slow network and a slow browser and a fast data iteration, the data might just got lost or got sold up altogether. So if you enable the like a chunk response with network acknowledgement, essentially, and it's because network acknowledgement may be slow, so your data keep sending, and then essentially like nothing showed up because it was so there's a depends on different type of systems. There's a pros and cons with a push. For the long-running Spark job, this may not be a problem, but for a short, small data, and sometimes these problems showed up. On the other hand, poll, if you have a poll and the data will not get stalled, usually you need a queue to store the data. So you get it evenly, nicely, every second you poll, every second you poll. But it's very hard to consume with multiple views because if you usually you take a data out, you take out of the queue, and then the next you want to see, you view the same data is already gone. So you cannot just use a very simple queue to do that. So there's a pro and con in both sides. We basically in this case we're using push. So the visualization side is again here is you can see different views of the same data side by side using push. And here, it's just like the same graph we've seen in the demo, essentially arrival time versus departure time, and arrival time versus the distance. And then there was a different cost iterations for k-means. And the data is using Plotly and D3. And so we're using Plotly to render a graph is quite simple. And actually literally just taking me half days to plot this. So essentially you define a cost. In my cases, I have a cost trace, essentially the bottom part, and the data you want to construct that into an array, and then you define the x, y, z, and the title, and then just say new plot. And so it was pretty simple. So and the sliding bar, just using D3 to do that. So in a summary, the training machine learning models involves a lot of experimentations, and so especially for the long training jobs, I don't want to just wait for 2-3 hours, find out it's either not convergent or it's already convergent and I'm still running and waiting. I rather just periodically peek what's going on. So is this thing already plateaued, and then let me just take the model and try something different. Or if it's not convergent, let me quickly stop this and do something. So sometimes I try to see what from, in real time, what each iteration, so what the machine learning training in process. So I need a way to visualize that. So this way, the approach we presented here is allow you to basically, quickly enable this. And you can see what the model has been training, whether it's convergent or not. You can stop iterations and save the model, and if it is good enough. I think that's all I have, and here's some Slack shares and other informations. So if you have questions, I can.
So I didn't quite catch, how do you send the Spark task information back into the web application? How did you register for this Spark task information update?
So before I start the Spark jobs, so we basically send the Spark, as part of the Spark configurations, we send a URI with essentially endpoints on our client side with Akka system, send to the Spark jobs. From there, And before I even start the Spark, calling the Spark, I actually do a handshake, essentially basically send a message back to the ping. It's like a ping message to the other end. The other end got it, send a message back. And so if you can get the ping bang back, means the communication is good. From then on, you can send any kind of messages because the archive message could be anything, so you can just send messages. So in this, for visualization, essentially the k-mean algorithms essentially say, okay, now I construct this message, send it over through this channel I just established. On the other end, and I'm saying, oh, this is a special type of a message means to this kind of visualizations. So we actually, I didn't say that. We have a hierarchy of messages. So there's application messages, there's a UI-specific display messages, there's a logging messages. So once I got the message on the client side, we basically do a pattern matching. Say, this one is for logging, go to all the log. And this one is for UI, we send it to display. And this particular part is for machine learning visualizations. So that goes to special type of things. So we at the beginning, so for example, for logging cases, not for visualization, so we can even redirect the print statement. So for example, if you do a Spark job, you do a print. Usually the print go to the yarn container log, and you have to see what did I print it. And we actually allow you to, if you print there, because we can redirect all the print statements back to our log as messages. So all your print directly sent to our client log outside the cluster. You can directly see the normal logging and say, oh, I print this. So all that stuff is done through this means.
But how do you do this redirection of prints?
Sorry?
How do you do this redirection of print commands?
So at the beginning of the Spark jobs, you can change the print streams. You can change the print streams too. Yeah, redirect it right to the log, and then after job's finished, you reset it back. Yeah.
Is there a similar thing you do for Spark context? Like the Spark context, when it starts a task, it does some notification. Do you do similar thing for Spark context, or how do you plug into this?
So the only difference is how do we start a Spark jobs. So we don't directly call Spark submit. We call, because it's a young cluster, we directly call Spark's young client.scala. So there, we basically, before you actually run that, we can set the application context right before the Spark job starts, and then right after. So, even before, we know when the Spark, starts and when it finishes. Before that even starts, we insert these application context at the beginning and at the end. On the Spark 1.1, we even modify the Spark code, and originally was thinking send a PR, but it was too much change, and it was the community decided that this is too much. What we did there is we modified the Spark Yarn client, and there at the beginning, before the Spark create a Yarn container, we create a Yarn application listener, essentially a callback. So that also give us other capabilities, like before the whole Spark starts, and because Yarn container just started, we know how much the container's max memory is, how many virtual cores you have. So and then when we call back to our Spark jobs, and our Spark job, this is just before the Spark starts, so we can, based on our data sets plus the container informations, to estimate how much memory is in the drivers automatically. In particular, at the beginning, Spark 1.1, Spark essentially is this. If you're asking for 8 gig of memory, I'll give you 8 gig. But if a container only have 6 gig, your Spark job plus overhead, it will over the max limit, I'm going to kill the job. So it's a Spark, as soon as it starts, it will get killed. So what we did is, based on the information, we can say, oh, you're asking way too much and beyond the capacity. So I give you a warning through this communication channel on the UI, basically say, you asking too much, but I'm not killing your job. I'm just reset it to a much lower, little lower than the max capacity, and then your job will run. But you get warning messages. So but it was too much changes, so we wrote it back. So there's other things we were essentially doing before and after the Spark job. So we starts. So I think this gives a lot of capabilities to any kind of other things. So the machine learning visualization is just one type of applications using that framework.
possible to like have multiple views as you get more dimensions and you start to...
Of course, you can literally, I'm just using plotly to do two-dimensional. You can use a three-dimensional, and then of course, you say, what about 6 or 9? Yeah, you have to essentially do whatever.
Pick and choose, can you pick and choose two to visualize against each other? Or?
Yeah, so this is up to you how you plot it, because the data is there. You can plot 3 views of two-dimensional or three-dimensional views, and this is up to you. Okay. Yeah, the data is pushed to the browser, and that's the rest of it just JavaScript.
Okay.
Yeah.
How big is the application?
Sorry.
How big the application is?
How big?
Yeah, is Hill first?
I don't think it's big. It's just I think if you're depends on what framework you choose. Here I'm using Akka because it was simple. I'm familiar with the Scala framework and Akka all that stuff. But of course, if you're not familiar with Akka, the ramping up is big. But you can choose other protocols. So for example, if you instead of using Akka, start Akka, sending Akka messages, if you're familiar with the netty, you can directly send in netty messages. That's the same thing. So it's just you choose the communication protocols. Yeah.
Is this going to be open source?
Well, what I built here is it will directly bake it into the Alpine systems. But if I have time, so I can just write it out. But right now, I'm not quite sure I have the time. All right. Oh, you have a question?
Yeah. Do you know is there similar effort going on like with the MLA in this part?
I don't think so. I talked to Sean Ray, and so I don't know. Sean Ray is the head of analytic teams and also the head of MLlib at the Databricks. So I don't know. I talked about these ideas, and hopefully they can open up more hooks so we can send in additional informations. And so I don't know if that will be in the plan or not. Yeah. Thank you very much.